Right now, as you listen to this sentence, the moment of your birth still exists. So does the moment of your death. Not as a memory, not as a prediction, as an actual point sitting somewhere in the universe, just as real as the chair you are sitting in or the phone in your hand. That is not a metaphor, and it is not mysticism. It is one of the most carefully tested conclusions in modern physics, and it comes from a place most people never expect. A set of equations Albert Einstein wrote down more than a century ago to explain something as mundane as how fast light travels. To understand how physicists arrived at a claim this strange, we have to start with something you already believe, whether you have ever thought about it or not. You believe that time flows. You believe that right now, this instant, is special. It is the one moment that is actually happening. Everything before it is gone. Everything after it has not happened yet. Physicists call this idea presentism, and for most of human history, it was never even treated as an idea. It was just obviously true, the same way it was once obvious that the sun circled the earth. Isaac Newton built the entire framework of classical physics on exactly this assumption. In his 1787 work, Newton described time as absolute, true, and mathematical, flowing equably without relation to anything external. In Newton's universe, there was one master clock ticking away in the background, the same for everyone, everywhere, no matter how fast they were moving or where they were standing. If two events happened at the same time for you, they happened at the same time for everyone else in the universe too. This was not just convenient, it matched everyday experience perfectly. When you and a friend agree that two things happened simultaneously, you never question whether someone standing in a different city or moving at a different speed would disagree with you. For around 200 years, this picture of time went essentially unchallenged. It explained the motion of planets, the fall of apples, the tides, the orbits of comets. Newtonian mechanics was, and still is, extraordinarily good at predicting how objects move in the world we experience directly. But underneath this successful framework, a much stranger question was quietly waiting to be asked. What exactly is light, and how fast does it actually travel relative to a moving observer? In the 1800s, physicists believed light was a wave, and like all the other waves they knew about, sound waves moving through air or ripples moving through water, they assumed light needed a medium to travel through. They called this hypothetical medium the luminiferous ether, an invisible substance that was supposed to fill all of space. If the ether existed, then the Earth, orbiting the Sun at close to 30 kilometers per second, should be moving through it. And if that were true, the speed of light should appear slightly different depending on whether you measured it in the direction the Earth was moving, or against it, the same way a sound wave measured from a moving car sounds different than one measured from a stationary point. In 1887, two American physicists, Albert Michelson and Edward Morley, built an extraordinarily precise instrument to detect this difference. Using an interferometer, a device that splits a beam of light in two, sends the halves along perpendicular paths, and then recombines them to detect even minuscule differences in travel time. They expected to measure how the Earth's motion through the ether changed the speed of light along different directions. They found nothing, no difference at all, regardless of the direction they measured, regardless of the time of year, regardless of how they oriented the equipment. The speed of light came out exactly the same every single time. This result, now known as the Michelson-Morley experiment, is often described as one of the most famous null results in the history of science, because what it failed to find turned out to be more important than almost anything it could have found. For nearly 2 decades, physicists tried to patch this result into the existing framework. Some proposed that objects physically contracted as they moved through the ether exactly enough to hide the effect. Hendrik Lorentz derived the mathematical transformations that would later become central to relativity, but he still assumed an underlying, undetectable ether. The puzzle sat there, unresolved, technically explainable with enough mathematical patchwork, but deeply unsatisfying. Then, in 1905, a 26-year-old patent clerk in Switzerland published a paper that did not try to save the ether at all. Albert Einstein simply took the null result at face value. He proposed that the speed of light in a vacuum is the same for every observer, no matter how fast that observer is moving, and no matter which direction they are moving in. Not almost the same. Exactly the same. Every time, for everyone. At first glance, this sounds like a small, technical fix. It is not. It is one of the most radical single sentences in the history of physics, because it directly breaks something that seems like basic common sense, the way velocities are supposed to add together. If you are on a train moving forward at 50 kilometers per hour, and you throw a ball forward at 10 kilometers per hour, someone standing still on the ground sees that ball moving at 60 kilometers per hour. Velocities add. This is true for balls, cars, and rockets, and it was true in Newton's universe without exception. But light does not behave this way. If you are on a spaceship moving at half the speed of light, and you turn on a flashlight pointed forward, someone watching from outside does not see the light moving at 1.5 times the speed of light. They see it moving at exactly the same speed as always, roughly 300,000 kilometers per second. No faster. For that to be true, something else in the equation has to give. And what gives, Einstein showed, is time itself. If the speed of light has to stay fixed for every observer, then measurements of time and space have to bend to keep that speed constant. This is the core insight of special relativity, and it produces 2 effects that have since been measured directly, repeatedly, and with extreme precision. The first is time dilation. A clock moving relative to you appears to tick more slowly than a clock at rest next to you. This is not an illusion caused by the light taking longer to reach your eyes. It is a genuine difference in how much time passes for each clock. The effect is tiny at everyday speeds, but it becomes significant as an object approaches the speed of light. This is not just theoretical. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners, then compared them to a reference clock that stayed on the ground. The flying clocks came back, reading a different elapsed time than the stationary one, and the difference matched the predictions of relativity to within the margin of experimental error. Today, this effect is not a curiosity confined to physics laboratories. It is something engineers must account for constantly. The satellites that make up the global positioning system orbit the Earth at roughly 14,000 kilometers per hour, fast enough that their onboard clocks run slower than clocks on the ground due to their speed. but they also sit farther from Earth's gravity, which makes their clocks run faster due to general relativistic effects. If engineers did not correct for both of these competing effects every single day, GPS positioning would drift by several kilometers within about 24 hours, rendering the entire system useless for navigation. The second effect is length contraction. An object moving relative to you appears shortened along its direction of motion. And the effect that matters most for our purposes, the one that leads directly to the idea that your birth and death already exist, is called the relativity of simultaneity. Here is the plain version of it. Two events that happen at the same time for one observer can happen at different times for another observer, if that second observer is moving relative to the first. This is not a matter of delayed light reaching one observer before the other. It is not a communication delay. It is a genuine disagreement about the order in which events occurred, and both observers are correct according to their own reference frame. Einstein illustrated this with a now famous thought experiment involving a moving train. Imagine a train moving at a significant fraction of the speed of light, with an observer standing exactly in the middle of one of the train cars. At the precise moment the observer passes a person standing on the platform outside, two bolts of lightning strike, one at the front of the train and one at the back, and critically, these two lightning strikes happen simultaneously according to the person standing on the platform. The person on the platform, standing exactly halfway between where the two strikes occurred, sees the light from both flashes arrive at the same instant, confirming for them that the two events were simultaneous. But the observer on the train experiences something different. Because the train is moving forward, the observer is moving toward the light coming from the front strike, and moving away from the light coming from the back strike. As a result, the light from the front reaches the observer on the train slightly before the light from the back does. And critically, this is not because the observer is confused about the timing due to light travel delays. After correcting for the distance the light had to travel and the speed at which it moved, the observer on the train would still conclude that the front strike happened first. From their own reference frame, moving at their own velocity, the two events genuinely did not happen at the same time. Two different observers, both making completely accurate measurements according to the physics of their own reference frame, arrive at two different mutually exclusive conclusions about which event happened first. There is no error here. There is no missing information that would resolve the disagreement if only someone measured more carefully. The disagreement is a fundamental feature of how space-time works, not a limitation of measurement. Now push this idea further, and you start to see why it has such enormous implications for the nature of time itself. In 1966, philosopher of science C.W. Rhettdike and physicist Hilary Putnam independently developed an argument that later became known as the Rhettdike-Putnam argument, and it was later refined and popularized by physicist Roger Penrose, who gave it a vivid illustration now called the Andromeda Paradox. Picture two people standing on a street, passing each other while walking in opposite directions. One is walking toward you, the other away. This tiny difference in velocity, walking speed, nothing close to the speed of light, is enough to shift what each of them considers to be happening right now on a distant planet. According to the mathematics of relativity, The Andromeda galaxy sits roughly 2.5 million light-years away. Because of the enormous distance involved, even a walking speed difference between the two people is enough to shift their respective planes of simultaneity. The set of events each of them would consider to be happening at this exact moment, by several days' worth of events happening on or near Andromeda. For the person walking toward Andromeda, right now, on that distant galaxy might include events several days further in the future compared to what right now means for the person walking away. Neither of them is wrong. Neither calculation contains an error. The disagreement is not resolved by better instruments or more careful observation. It is baked directly into the geometry of space-time. Penrose used this thought experiment to argue for something startling. If two people standing on a sidewalk, walking at ordinary human speeds, can have genuinely different, equally valid opinions about what is happening right now, light years away, then the idea of a single universal now that applies to the whole universe cannot be correct. There is no privileged present moment. There is no cosmic clock ticking away the one true now for everyone, everywhere. What counts as the present depends entirely on your state of motion. This might sound like a curiosity limited to hypothetical scenarios involving distant galaxies, but the logic scales down perfectly well too. It applies just as rigorously to any two events anywhere at any distance, including events much closer to home, including the events of your own life. This is the seed of the idea that gives this topic its name. If simultaneity is relative, if there is no single agreed upon now shared by the whole universe, then the boundary between past, present, and future cannot be a fundamental feature of reality the way we intuitively believe it is. It has to be something else, something more like a fixed structure, a landscape rather than a flow. To understand what that structure actually looks like, we need to introduce the mathematical framework that made sense of Einstein's work in the first place, one built not by Einstein but by his former mathematics professor. In 1908, the mathematician Hermann Minkowski gave a lecture in which he reframed Einstein's special relativity in purely geometric terms. His opening line has become one of the most quoted statements in the history of physics from now on. Space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski showed was that space and time are not two separate things that happen to interact. They are two aspects of a single four-dimensional structure, now called space-time. In this framework, every object, every particle, every person does not simply exist at a point in three-dimensional space. It traces out a path through four-dimensional space-time called a whirlline that includes its entire history from its beginning to its end. Think of your own world line as a long, unbroken thread. One end of that thread is the moment of your birth. The other end is the moment of your death. Everything in between, every event of your life, every breakfast, every conversation, every heartbeat is a specific point along that thread, fixed at a specific location in space-time. In Minkowski's geometric picture, this thread does not appear or disappear as now moves along it. It simply exists all at once. The way a physical road exists all at once, even though a car driving along it only occupies one section of it at any given instant. This is where the phrase block universe comes from. If every event in the history of the universe, past, present, and future, exists as a fixed point within this four-dimensional structure, then the universe is not something that is happening. It is something that simply is, a single, unchanging, four-dimensional block containing everything that ever was and everything that ever will be. Time does not flow through this block. Time is one of the dimensions of the block itself, laid out much the way length, width, and height are laid out in ordinary space. This picture directly explains why the relativity of simultaneity works the way it does. If now is not an objective feature of the universe, but rather something that depends on your particular path through space-time, your particular world line, and your particular velocity, then it makes perfect sense that two different observers can disagree about which events count as the present. They are essentially slicing the four-dimensional block along slightly different angles, and each angle picks out a different set of events as simultaneous. Under this framework, the moment of your birth is not something that used to exist and has since been destroyed by the passage of time. It is a location, a fixed point in the four-dimensional structure of the universe, just as real and just as permanent as the location of Mount Everest or the surface of the moon. The same is true of the moment of your death, wherever and whenever that point on your world line happens to be. It already exists in the block, occupying its own fixed coordinate in spacetime, regardless of whether your consciousness has arrived there yet from your own subjective perspective. This is the precise sense in which physicists who take the block universe seriously say that you are, in a very real sense, born and die at the same time. Not that these two events happen simultaneously in the ordinary sense of that word, but that both events exist with equal permanent reality within the structure of space-time. Neither one is more real than the other. Neither one is privileged by some special property that the other lacks. Your birth is not more real because it is in the past relative to your current position along your world line, and your death is not less real because it has not yet been reached by your current position along that same world line. Both are simply coordinates, fixed, unchanging, always there. It is worth pausing here to be precise about what this claim does and does not say, because it is easy to overstate it into something closer to mysticism than physics. The block universe view does not claim that you are simultaneously experiencing your birth and your death right now, in some ghostly, overlapping way. Your conscious experience, whatever its ultimate nature turns out to be, still appears to unfold along your world line in a specific order from birth toward death, one moment following another in the sequence you are familiar with. What the block universe view claims is something more subtle and, in a way, more radical, that the passage of time you experience, the sense that the present moment is special, that the past is gone and the future is not yet real, might not correspond to any objective feature of the universe at all. It might be something more like an internal, biological, or perceptual phenomenon, generated by the way conscious minds process information along their world line, rather than a fundamental truth about the structure of reality itself. Philosophers who study the nature of time have a formal name for the ordinary, intuitive belief that the present is objectively special. They call it the theory of time, following a distinction introduced by the philosopher J.M.E. McTaggart in 1908, the same year as Minkowski's famous lecture. Under the theory, events genuinely change their status. An event that is currently in the future will, at some point, become present and then recede into the past. This change in status, from future to present to past, is treated as objectively real, not just a feature of how humans happen to describe events. The opposing view, the B theory of time, holds that events do not change their status at all. Under the B theory, events are simply ordered relative to one another, earlier or later, but no event is ever objectively the present in any absolute sense. Whether an event counts as past, present, or future depends entirely on which point along a world line you are asking the question from. Exactly the way whether a city counts as near or far depends entirely on where you are standing when you ask. The block universe picture that emerges from Minkowski's geometric interpretation of relativity fits naturally with the B theory. Special and general relativity are two most well-tested and successful physical theories, do not contain any equations that single out a privileged objective now. The equations treat all points in spacetime. Nothing in the mathematics distinguishes the moment you were born, the moment you are reading this sentence, or the moment you will eventually die, as more or less real than any other point in spacetime. All are simply coordinates within the same four-dimensional structure. This is precisely why so many physicists, when pressed on the question, describe the flow of time as one of the deepest remaining mysteries in physics, not because they doubt relativity, but because relativity itself provides no mechanism for it. Einstein himself, in a letter written in 1955 to comfort the family of his recently deceased close friend, Michel Bess, wrote that people like them, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. He died himself only a few weeks after writing those words. It remains one of the more haunting personal reflections from one of the founders of the very framework that produced this conclusion. It would be inaccurate to present the block universe view as a settled, unanimous conclusion accepted by every physicist and philosopher. It is the dominant interpretation among physicists who work directly with relativity, largely because it falls out so naturally from the mathematics without requiring any additional assumptions. But the philosophical debate over the true nature of time remains genuinely active, and it is worth understanding the main alternative positions, because each one takes the physics seriously while drawing a different conclusion from it. The first alternative is presentism, the view that only the present moment is real. Under strict presentism, the past no longer exists in any sense, and the future does not yet exist in any sense. Only now is real, full stop. The difficulty presentism runs into is the relativity of simultaneity we already covered. If there is no single objective now shared across the entire universe, if different observers moving at different velocities genuinely disagree about which set of events counts as the present, then presentism has to explain what the present even refers to on a cosmic scale. Some presentist philosophers respond by arguing that the present should simply be defined relative to each observer's own reference frame, giving up on the idea of a single universal present in exchange for keeping a form of presentism that applies locally. Critics argue this move quietly abandons what made presentism appealing in the first place. The idea of one shared, objective, present moment for the whole universe. The second alternative is the growing block universe, a position most closely associated with the philosopher C.D. Broad in the 1920s. Under this view, the past and present are both real and fixed, exactly as in the standard block universe picture. But the future genuinely does not exist yet. New moments are constantly being added to the block, like new pages being written onto the end of a book that already has a beginning and a middle, but no fixed ending. This view tries to preserve the intuitive sense that the future is open and undetermined, while still explaining why the past feels fixed and unchangeable. Critics point out that the growing block view has to explain what makes the present, the leading edge where new moments are being added, so special when relativity gives us no physical mechanism that could single out one particular slice of spacetime as the growing edge rather than any other. The third position is eternalism, the formal name for the standard block universe view we have already discussed at length. Past, present, and future are all equally real, and the passage of time is not an objective feature of the universe, but rather a feature of conscious experience. This is the view most naturally supported by the mathematics of special and general relativity, since it requires no extra assumptions beyond the equations themselves, no privileged reference frame, and no special mechanism for adding new moments to reality. Its critics, meanwhile, argue that it fails to adequately explain something almost everyone takes to be obviously true from direct experience: that time genuinely does seem to pass, that the future feels open in a way the past does not, and that this feeling demands an explanation beyond simply calling it an illusion generated by the brain. This disagreement is not a matter of physicists being unable to do the math. All three camps agree completely on the equations of relativity and on every experimental result relativity has ever produced. The disagreement is about what those equations and that experimental success actually tell us about the deep nature of reality, a question that sits at the boundary between physics and philosophy, where the data alone cannot fully settle the argument. If eternalism is correct, and past, present, and future are all equally real points fixed within a four-dimensional block, a natural question follows immediately. Why does time feel like it has a direction at all? Why do we remember the past but not the future? Why can an egg break into pieces on the floor, but a broken egg never spontaneously reassembles itself and jumps back onto the counter? If all moments are equally real and equally fixed, nothing about the fundamental structure of space-time itself seems to demand that things should only ever unfold in one particular order. This puzzle is called the arrow of time, and remarkably, the deepest laws of physics we know, including Newton's laws, Einstein's relativity, and the core equations of quantum mechanics, are almost entirely time-symmetric. If you took a video of two billiard balls colliding and played it backward, the reversed footage would still perfectly obey the underlying laws of motion. Nothing in the equations themselves forbids the reversed sequence of events. And yet, in the world we actually experience, some processes clearly only ever happen in one direction. Eggs break but do not unbreak. Coffee cools down in a room but does not spontaneously heat up by pulling energy from the surrounding air. People age, but do not grow younger. The explanation physicists give comes not from the fundamental laws of motion themselves, but from thermodynamics, and specifically from a quantity called entropy, first developed by the physicist Ludwig Boltzmann in the 1870s. Entropy is, roughly speaking, a measure of how many different microscopic arrangements of a system correspond to the same overall macroscopic appearance. An unbroken egg has extremely low entropy because there are relatively few ways to arrange its molecules that would still look like an intact egg. A broken egg has enormously higher entropy because there are vastly more ways to arrange the same molecules into a scattered mess that would still look like a broken egg on the floor. The second law of thermodynamics states that in any closed system, entropy tends to increase over time, simply because there are overwhelmingly more high entropy arrangements available than low entropy ones, and random processes are statistically far more likely to end up in one of the many high entropy states than in one of the comparatively rare low entropy states. This gives us a direction of time defined not by some deep law of the universe demanding it, but by simple statistics. The future is the direction in which entropy increases, and the past is the direction in which entropy was lower. This is sometimes called the thermodynamic arrow of time, and many physicists, including Sean Carroll and others who study cosmology closely, argue it is deeply connected to the psychological arrow of time as well. Our subjective sense that we remember the past and not the future. Memory, after all, requires physically encoding information in a low-entropy, ordered form, such as the specific arrangement of neurons in a brain. Because entropy only reliably increases in one temporal direction, it is only possible to form reliable memories of the lower entropy past, which remains fundamentally more difficult to encode in an ordered way. But this explanation raises an even deeper question that remains genuinely unresolved. Why did the universe start out in such an extraordinarily low entropy state in the first place? If the standard cosmological picture is correct, and the universe began roughly 13.8 billion years ago in an extremely hot, dense, and, crucially, extremely low entropy configuration, then everything that follows, stars forming, planets cooling, life evolving, memories forming, all of it depends on that single, remarkably improbable starting condition. Physicists refer to this as the past hypothesis, and explaining why the universe began in such a special, low-entropy state remains one of the open frontiers of cosmology, closely tied to ongoing research into the very earliest moments after the Big Bang. So far, everything we have covered comes from special relativity, the version of Einstein's work that deals with objects moving at constant velocities without accounting for gravity. In 1915, Einstein extended these ideas dramatically further with general relativity, a theory of gravity in which massive objects do not pull on each other through some invisible force acting at a distance, but instead curve the very fabric of space-time around them, and other objects simply follow the straightest possible path through that curved geometry. A planet orbits a star not because the star is reaching out and grabbing it, but because the star's mass bends space-time into a shape that makes an orbit the natural straight-line path to follow. General relativity did not soften the block universe picture. If anything, it deepened it and produced one of the strangest and most underappreciated results in the entire history of theoretical physics. In 1949, the mathematician and logician Kurt Gödel, working alongside Einstein at the Institute for Advanced Study in Princeton, discovered an exact solution to Einstein's field equations describing a hypothetical rotating universe. In Gödel's solution, the entire universe spins, and this rotation warps spacetime so severely that it becomes possible, mathematically, for an object to travel along a path through spacetime that loops back on itself, arriving at a point in its own past. Physicists call such a path a closed time-like curve. In Gödel's rotating universe, an astronaut could, in principle, board a spacecraft, travel along a sufficiently long path, and return not just to the same location in space, but to an earlier moment in their own timeline before they had even left. Gödel did not believe our actual universe rotates in this way. And in fact, all the observational evidence we have gathered since suggests it does not. But that was never really his point. His argument was philosophical, and it was aimed directly at the presentist and growing block positions we discussed earlier. If the equations of general relativity, our best and most rigorously tested theory of gravity, permit universes in which the very concept of before and after can become tangled and circular, then time cannot be a simple, universal, one-directional flow built into the fundamental structure of reality. It has to be something that emerges from the specific geometry of a particular universe, rather than something imposed on all possible universes from outside. Einstein himself, upon reviewing Gödel's solution, wrote that it would be interesting to establish whether or not such rotating universes are excluded on physical grounds, a question that, in various forms, cosmologists continue to investigate. There is a related, and perhaps even more intuitive, way general relativity reshapes our sense of time. Gravitational time dilation. Clocks closer to a massive object, where space-time curvature is stronger, run measurably slower than clocks farther away, where space-time is flatter. This has been confirmed with extraordinary precision. In 2010, physicists at the National Institute of Standards and Technology showed that two atomic clocks, separated in height by just 33 centimeters, roughly the height of a single stair-step, ticked at slightly different rates due to the tiny difference in gravitational potential between them. A person who spends their life living on the top floor of a tall building will, over many decades, age by a genuinely measurable, if vanishingly small, amount more than a person who spends their life at sea level, purely because of the weaker gravitational field at greater height. Once again, this is not a curiosity confined to laboratories. It has direct, practical consequences. GPS satellites, as mentioned earlier, orbit far enough from Earth that the weaker gravity they experience causes their clocks to run measurably faster than identical clocks on the ground. And this effect has to be corrected for daily, alongside the opposite effect caused by the satellite's orbital speed, or global navigation systems would fail within a single day. Relativity reshapes our understanding of time dramatically, but it is far from the only branch of physics that treats time as something other than the simple, flowing background we intuitively imagine. Quantum mechanics, the theory describing the behavior of particles at extremely small scales, introduces its own deeply strange complications. And when physicists attempt to combine quantum mechanics with general relativity into a single, unified theory of quantum gravity, time becomes even harder to pin down. In the standard formulation of quantum mechanics, time plays a somewhat unusual role compared to the other quantities in the theory. Position, momentum, and energy are all treated as quantum operators, mathematical objects that can be uncertain, that can exist in superpositions of multiple values at once, and that only take on definite values upon measurement. Time, by contrast, is usually treated as an external parameter, a simple, classical background variable that is not itself subject to quantum uncertainty. This asymmetry has bothered physicists since the early development of the theory, because it treats time fundamentally differently from every other physical quantity. Even though relativity insists that time and space should be treated on equal footing, the problem becomes especially acute when physicists attempt to write down a quantum theory of gravity itself, applying quantum principles to the geometry of spacetime described by general relativity. In 1967, physicists Bryce DeWitt and John Wheeler derived an equation, now known as the Wheeler-DeWitt equation, intended to describe the quantum state of the entire universe. The equation works mathematically, but it comes with an extraordinarily strange feature. There is no time variable in it at all. The equation describes the universe's quantum state as fundamentally timeless, a single, static configuration with no explicit variable representing the passage of time whatsoever. Physicists refer to this puzzle as the problem of time in quantum gravity, and it remains one of the deepest unresolved issues at the intersection of quantum mechanics and general relativity. Several physicists and philosophers have proposed radical responses to this puzzle. The physicist Julian Barbour, in his 1999 book, The End of Time, argued that we should take the Wheeler-DeWitt equation completely at face value. There is no such thing as time at the most fundamental level of reality, only an enormous collection of possible configurations of the universe, which he called nows, each one a complete, static arrangement of everything in existence at that configuration. Under Barbour's view, what we experience as the flow of time is really just our consciousness moving through, or rather being instantiated within a sequence of these fixed configurations, each of which contains within itself the appearance of a history leading up to it, including our memories, without there being any actual, external flow connecting one configuration to the next. A different, somewhat less extreme proposal comes from the physicist Carlo Rovelli, a leading figure in loop quantum gravity, one of the major candidate theories attempting to unify quantum mechanics and general relativity. In his book, The Order of Time, published in 2018, Rovelli argues that time is not a fundamental feature of reality at all, but rather an emergent, approximate concept that arises from the statistical and thermodynamic behavior of large systems of particles, closely tied to the entropy arguments we covered earlier. He has developed, along with physicist Ailing Kahns, an idea called the thermal time hypothesis, which suggests that the specific direction and flow of time we experience might be a byproduct of our own limited, coarse-grained perspective on a universe that, at its most fundamental quantum level, has no intrinsic notion of time flowing at all. In Ravelli's own words, paraphrased rather than quoted directly, time is not something that exists independently of the physical processes we use to measure it, but rather something that emerges from the relationships between those processes. These are not fringe positions. They come from physicists working at the very center of contemporary theoretical physics, publishing in peer-reviewed journals and leading major research groups. And yet, despite decades of work, there is still no consensus theory of quantum gravity, and correspondingly, no consensus answer to the deepest version of the question we started with, whether time, at the most fundamental level nature operates on, exists as anything more than a convenient approximation useful only at the much larger, coarser scales where humans happen to live and think, given how strange and unsettled the physics turns out to be. It is worth turning the question around and asking a more personal one. If time does not flow the way it feels like it flows, why does it feel that way at all? Why does the present moment feel so overwhelmingly special, urgent, and singular, if physics gives us no particular reason to think it is? Part of the answer comes from neuroscience and psychology rather than physics directly. Human consciousness does not perceive reality as a continuous, unbroken stream. Instead, the brain constructs the experience of now out of discrete windows of processed information, sometimes called the specious present, a term introduced by the psychologist E.R. Clay in the 1880s and later developed further by the philosopher William James. Experiments in cognitive neuroscience suggest this window is roughly 2 to 3 seconds wide, the rough duration over which the brain integrates incoming sensory information into a single, unified experience of right now. Even though the raw sensory information arrives continuously, moment by moment, with no such packaging. This matters because it means the felt experience of the present moment is, at least in part, a construction, an interpretation layered on top of whatever is physically happening, rather than a direct, unmediated readout of some fundamental feature of the universe. The brain also has strong reasons, evolutionarily speaking, to construct experience this way. An organism that could not distinguish between memories of the past and predictions about the future, and that did not experience a strong pull toward anticipating and reacting to what happens next, would struggle to survive and reproduce compared to one that did. The subjective urgency of now, in other words, may be less a window into the deep structure of reality and more a feature that evolution built into conscious minds because it was useful for staying alive. This connects to a question many people find genuinely unsettling once they sit with the implications of the block universe seriously. What happens to free will if the future already exists, fixed and unchanging, somewhere in the four-dimensional structure of space-time? Philosophers who accept eternalism generally respond in one of two ways. Some argue that eternalism is fully compatible with free will, a position sometimes called compatibilism, on the grounds that your choices are still genuinely yours, caused by your own reasoning, desires, and deliberation, even if the outcome of that deliberation happens to already exist as a fixed point in space-time from an external, four-dimensional perspective. Under this view, saying the future already exists is not fundamentally different from saying your past choices already happened, a fact that does not usually feel like it robs those past choices of having been genuinely yours to make at the time. Others argue that eternalism does pose a genuine challenge to certain strong notions of free will, particularly ones that require the future to be genuinely open and undetermined until the moment a choice is actually made, and that a fully consistent eternalist has to accept some version of determinism, even if the deterministic outcome still flows entirely from the physical processes happening inside your own brain, rather than from any external coercive force. This debate remains philosophically unresolved, in large part because it touches questions like the true nature of consciousness and the true nature of causation that physics alone cannot fully settle. What physics can tell us, with a very high degree of confidence, is the geometric structure of space-time itself, that it does not contain a privileged, universal present moment, and that events across time appear, from the perspective of the equations, to have the same basic ontological status as events across space. What physics cannot yet tell us is exactly how consciousness, whatever it ultimately turns out to be, relates to that four-dimensional structure, or why it seems to move through it in the particular one-directional way it does. If a claim this strange, one built on more than a century of rigorously tested physics rather than speculation, is the kind of thing that changes how you think about a single afternoon, it is worth sitting with for a while rather than rushing past it. And if you want more explanations like this one, built carefully from real research rather than exaggerated for effect, following along and sharing it with someone who would find it interesting is the simplest way to keep this kind of careful science communication going. To really understand why the block universe picture holds together so well, it helps to look at one more concept from relativity, the light cone, which describes exactly which events in spacetime can possibly affect or be affected by any given point. Imagine standing at a single point in spacetime, a specific location at a specific moment, because nothing can travel faster than the speed of light, according to relativity. There is a strict limit on which other events could possibly have influenced you, and which events you could possibly influence in return. If you drew every possible path light could take away from your position in every direction over time, that expanding sphere of light traces out what physicists call your future light cone, the complete set of events you could, in principle, still affect. Trace the same construction backward in time, and you get your past light cone, the complete set of events that could, in principle, have affected you. Everything outside both of these cones, everything too far away to have exchanged even a light signal with your current position, given the time available, falls into a region physicists sometimes call elsewhere. Events in this elsewhere region are causally disconnected from you entirely. Nothing that happens there right now, wherever now even means for a distant event like this, can affect you until enough time passes for light or some other signal to reach you, and nothing you do right now can affect what happens there until an equivalent amount of time has passed in the other direction. This structure of past light cones, future light cones, and a causally disconnected elsewhere in between, turns out to be completely consistent across every observer, no matter how fast they are moving or in what direction, even though observers can disagree about simultaneity. about which distant events count as happening right now. They never disagree about causal order within a light cone. If event A is inside the past light cone of event B, meaning A could have physically caused B, every observer, moving at any velocity, will agree that A happened before B. The order of cause and effect is preserved, absolutely. What becomes relative, what depends on your motion, is only the ordering of events that are causally disconnected from each other. Events sitting in each other's elsewhere region, where no signal has had time to travel between them. This is an important nuance because it clarifies exactly what the relativity of simultaneity does and does not scramble. It does not throw causality into chaos. Effects still always come after their causes, for every observer, without exception. What it scrambles is only the notion of a single universal now stretching across the entire universe simultaneously, connecting events that have no causal relationship to each other at all. Your birth caused countless later events in your life, including the moment you are hearing this sentence right now, and every observer in the universe, regardless of their velocity, would agree on that causal ordering. What no observer can claim is a privileged, objective answer to the question of what is happening on a planet in a distant galaxy at this exact moment, because that planet and your current position are, for all practical purposes, causally disconnected from each other, sitting in each other's elsewhere. This causal structure is precisely what makes the block universe picture mathematically coherent rather than an arbitrary or unfalsifiable philosophical add-on. The geometry of light cones is not an interpretation layered on top of relativity. It falls directly out of the equations themselves, confirmed by nearly a century's worth of experiments in particle physics, astronomy, and precision timekeeping. The four-dimensional block is not a metaphor invented to make a philosophical point sound more dramatic. It is closer to the plainest, most literal reading of what the mathematics of spacetime actually describes. None of this would carry much weight if it were purely theoretical. So it is worth walking through exactly how thoroughly these predictions have been tested experimentally, because the confirmations go far beyond the atomic clock experiment mentioned earlier. One of the clearest confirmations of time dilation comes from particles called muons, unstable subatomic particles that are constantly created when cosmic rays from space strike the upper atmosphere, roughly 15 kilometers above the Earth's surface. Muons decay extremely quickly, with an average lifetime, when measured at rest in a laboratory, of about 2 microseconds. Given that lifetime, and given that even traveling close to the speed of light, a muon should only be able to travel roughly 600 meters before decaying. Far too short a distance to reach the Earth's surface from 15 kilometers up, and yet, physicists detect enormous numbers of muons at ground level, far more than classical physics would predict should survive the trip. Special relativity resolves this cleanly. From the Earth's frame of reference, the muons are moving at close to the speed of light, and their internal clocks, the process that governs their decay, run slower due to time dilation, allowing many more of them to survive long enough to reach the ground than a naive, non-relativistic calculation would predict. From the muon's own frame of reference, an equally valid way to describe the same physical situation, its own lifetime has not changed at all, but the 15 kilometers of atmosphere above it has become dramatically shortened due to length contraction, allowing it to cross that shortened distance well within its normal lifespan. Both descriptions, one invoking time dilation and one invoking length contraction, are physically equivalent, and both are needed to fully understand the same phenomenon from two different, equally legitimate reference frames. This experiment has been repeated and confirmed with high precision since the 1940s, and it remains one of the standard demonstrations used in university physics courses, specifically because it is such a clean, direct confirmation of relativity using naturally occurring particles rather than expensive custom-built equipment. Gravitational time dilation has its own famous early confirmation as well. In 1959, physicists Robert Pound and Glenn Rebka conducted an experiment at Harvard University, now known as the Pound-Rebka experiment, in which they measured the tiny shift in the frequency of gamma-ray photons as they traveled up or down a 22.5-meter tower. General relativity predicts that a photon climbing out of a gravitational well should lose a small amount of energy, causing its frequency to shift slightly toward the red end of the spectrum, an effect called gravitational redshift, while a photon falling into a gravitational well should gain energy and shift toward the blue end of the spectrum, despite the extraordinarily small predicted effect. Roughly 2 parts in 10 to the 15th, Pound and Rebka were able to measure it using a clever technique that exploited a property of certain atomic nuclei, and their results matched Einstein's prediction to within about 10%, a remarkable achievement for an experiment conducted on a university campus rather than in space. Since then, the precision of these tests has improved dramatically. Modern optical atomic clocks, the most precise timekeeping devices ever built, are now sensitive enough to detect gravitational time dilation over height differences of just a few centimeters, confirming Einstein's predictions to a level of precision Einstein himself likely never imagined would be achievable. Every single one of these experiments, across more than a century of increasingly sophisticated technology, has confirmed the same underlying picture that time is not a fixed universal background, but a genuinely flexible physical quantity, one that bends differently depending on your speed and your position within a gravitational field, exactly as the mathematics of the block universe requires it to. Zooming out from individual particles and clocks to the entire universe, cosmology adds its own layer to this picture, and it is where the arrow of time question connects most directly to the deepest open problems in physics. According to the standard model of cosmology, the universe began roughly 13.8 billion years ago in an extraordinarily hot, dense state and has been expanding and cooling ever since, an event popularly called the Big Bang. This is not a single-point explosion happening at one location within a pre-existing empty space, a common misconception. It is better understood as space itself expanding uniformly everywhere at once, stretching the distances between distant galaxies over time, a process confirmed observationally by the redshift of light from distant galaxies, first measured systematically by the astronomer Edwin Hubble in 1929, and later given overwhelming additional support by the discovery of the cosmic microwave background radiation in 1965, the faint, ancient afterglow of the early universe, still detectable today, uniformly in every direction we look. The early universe, in this standard picture, was in an extraordinarily low entropy state, differing from place to place by only about 1 part in 100,000. As the universe has expanded and evolved, gravity has pulled matter together into increasingly clumped, structured arrangements, stars, galaxies, planets, and eventually, on at least one of those planets, the complex chemistry that led to life. Each of these steps, counterintuitively, actually increases the total entropy of the universe overall, even though local pockets, like a forming star or a living organism, become more ordered in the process, because the energy released in forming these structures, radiated away as heat and light, spreads out into the surrounding environment in an even more disordered way than it started. This gives cosmology its own arrow of time, sometimes called the cosmological arrow of time, defined simply by the direction in which the universe is expanding and its overall entropy is increasing. Current observations, first reported in 1998 by 2 independent teams of astronomers studying distant supernovae, indicate that the expansion of the universe is not merely continuing, but actually accelerating, driven by a poorly understood component of the universe termed dark energy, which appears to make up roughly 68% of the total energy content of the universe, according to the most recent precision measurements. If this accelerating expansion continues indefinitely, and current data offers no strong indication that it will not, the long-term future of the universe, sometimes called heat death, or more technically the Big Freeze, involves stars gradually exhausting their nuclear fuel over trillions of years, galaxies drifting so far apart that they become causally disconnected from one another, and eventually, on timescales almost impossible to intuitively grasp, encompassing periods vastly longer than the current age of the universe, even black holes evaporating away entirely through a slow quantum process predicted by the physicist Stephen Hawking in 1974, called Hawking radiation. In this far future scenario, entropy approaches its maximum possible value, and with no meaningful thermodynamic gradients left to drive any physical process, the arrow of time itself effectively loses its meaning. Not because time stops existing in any structural sense within the block universe, but because there would be nothing left capable of distinguishing one moment from the next. It is worth being clear that this cosmological endpoint remains a prediction based on current data and current models, not an established certainty. The nature of dark energy remains one of the largest unresolved puzzles in physics, and any refinement of our understanding of it could meaningfully change these long-term projections. What does not change under any of these scenarios is the underlying block universe structure itself, whatever ultimately happens across the full span of cosmic history. Every one of those moments, however distant, would already occupy its own fixed coordinate within the same four-dimensional block that contains the moment of your birth and the moment of your death. Black holes offer one of the most extreme and most instructive illustrations of how flexible time becomes under general relativity, and they connect several of the ideas already covered into a single, vivid picture. A black hole forms when an extremely massive object, typically the collapsed core of a dying star, far more massive than our Sun, compresses under its own gravity into a region so dense that not even light can escape from within a certain boundary, called the event horizon. Near this boundary, gravitational time dilation, the same effect confirmed on a tiny scale by the Pound-Rebka experiment and by GPS satellites, becomes extreme rather than subtle. If you were to watch a clock or a person or any object falling toward a black hole from a safe distance away, you would never actually see it cross the event horizon, at least not in any finite amount of your own observed time. As the object approaches the horizon, the light it emits takes longer and longer to climb back out of the increasingly steep gravitational well. So from your perspective, the object appears to move more and more slowly, its light growing dimmer and more redshifted, effectively freezing at the boundary of the horizon forever. From your point of view, from the perspective of the object actually falling in, however, nothing particularly dramatic happens at the event horizon itself, at least for a sufficiently large black hole. The infalling observer crosses the horizon in a perfectly ordinary, finite amount of their own experienced time, continuing onward toward the black hole's center, called the singularity, a region where general relativity's equations, remarkably, predict that the mathematical description of space itself effectively runs out. With our current physical theories unable to say with confidence what actually happens there. This produces one of the more genuinely mind-bending features of black hole physics: two different, equally valid descriptions of the same physical event, one in which an object never crosses the horizon within any finite time as observed from outside, and one in which the same object crosses the horizon in perfectly ordinary finite time from its own perspective, coexisting without contradiction, because, exactly as with the relativity of simultaneity discussed earlier, there is no single, universal, correct answer to when an event happens that applies equally to every observer, regardless of their position and state of motion. Black holes also deepen the connection between time and entropy. In the early 1970s, the physicist Jacob Bekenstein proposed, and Stephen Hawking later confirmed mathematically, that black holes possess an enormous amount of entropy, proportional not to their volume, as one might intuitively expect, but to the surface area of their event horizon. This discovery, combined with Hawking's later prediction that black holes slowly radiate away energy through a quantum process and will eventually evaporate entirely, has become a central touchstone for physicists attempting to unify quantum mechanics with general relativity, precisely because it sits at the intersection of gravity, thermodynamics, and quantum theory. The same three domains that each, in their own way, shape our understanding of what time actually is. The connection between black holes and information has produced its own long-running puzzle, sometimes called the black hole information paradox. If a black hole eventually evaporates away completely through Hawking radiation, a fundamental question arises. What happens to the information about everything that ever fell into it? Quantum mechanics strongly suggests that information cannot simply be destroyed. Yet the simplest picture of Hawking radiation suggests exactly that. Resolving this tension has occupied some of the most prominent theoretical physicists for decades. And while several proposed resolutions exist, including ideas involving quantum entanglement between the radiation and the black hole's interior, no complete universally accepted resolution has yet emerged, making it one of the clearest live examples of how much remains genuinely unknown at the boundary between our two most successful physical theories. There is a newer, more experimental frontier in this story as well, one that has developed largely within the last 15 years, and it pushes the question of causal order in an entirely different direction than relativity does. Quantum mechanics allows for a strange phenomenon called superposition, in which a particle can exist in a precisely defined mathematical sense, in a combination of multiple states at once, only settling into one definite state upon measurement. Physicists working on the foundations of quantum theory, including a research group led by physicist Čáslav Bruckner at the University of Vienna, have designed and carried out experiments demonstrating something called indefinite causal order, using a theoretical device called the quantum switch. In a normal, everyday process, if event A causes event B, that ordering is fixed. A happens, and then B happens as a result, and every observer, per the light cone structure discussed earlier, agrees on that order. In a quantum switch experiment, however, physicists arrange a quantum system so that a photon passes through to operations, conventionally labeled Operation A and Operation B, in a genuine quantum superposition of both possible orders at once, A then B and B then A, simultaneously, in a way that is not simply an experimenter's uncertainty about which order occurred, but a genuine physical superposition of both causal orders, confirmed through subsequent measurements that would be impossible to reproduce if the photon had actually gone through the operations in one fixed order or the other. These experiments, first realized in the laboratory around 2015, and refined considerably since, do not overturn relativity or claim that effects can precede their causes in any straightforward sense. What they demonstrate is that, at the quantum scale, even the notion of a single, fixed causal order between events, an idea relativity otherwise treats as sacred and unchangeable within a light cone, can become blurred and probabilistic in carefully engineered quantum systems. Researchers in this field see indefinite causal order as a potentially important clue for physicists trying to build a working theory of quantum gravity, since any such theory will eventually need to describe situations like the interior of black holes or the earliest moments after the Big Bang, where both quantum effects and strong gravitational effects on space-time structure become significant simultaneously, and where our current separate theories of quantum mechanics and general relativity, each excellent within its own domain, are known to break down or contradict each other. This is a genuinely active area of both theoretical and experimental research, not a settled result with clear implications for everyday causality, but it illustrates something important about the state of physics. Today, the closer researchers look at the foundations of causal order and the flow of time, whether through the geometric lens of relativity or the probabilistic lens of quantum mechanics, the less these foundations resemble the simple, intuitive picture of a single universal clock ticking steadily forward that most people, quite reasonably, assume describes reality by default. None of this is actually a new question, even though the mathematics behind it, long before Einstein, long before Minkowski, human thinkers were already arguing over whether time was a genuine feature of a changing world, or an illusion layered over a deeper, unchanging reality. And it is worth briefly connecting the modern physics back to that much older debate, because the resemblance is striking. In ancient Greece, the philosopher Heraclitus, working around 500 years before the Common Era, is famously associated with the idea that everything is in constant flux, that you cannot step into the same river twice, because both the river and the person stepping into it have changed by the second attempt. For Heraclitus, change and the passage of time were the most fundamental features of reality, not an illusion layered on top of something more stable. Around the same period, the philosopher Parmenides argued for something close to the opposite position. Parmenides held that true reality is a single, unchanging, eternal whole, and that the apparent change and motion we perceive through our senses is, in some important sense, an illusion, a mistaken impression generated by human perception rather than a reflection of how reality actually is at its deepest level. His student, Zeno of Ilia, developed a famous series of paradoxes, including the well-known paradox of Achilles and the tortoise, specifically to argue that motion itself, when examined logically and carefully, leads to contradictions, and should therefore be treated with far more suspicion than our intuitions suggest. It is a genuinely striking historical coincidence, or perhaps not a coincidence at all, that the modern eternalist position derived from relativity echoes Parmenides far more closely than it echoes Heraclitus, roughly 2,500 years later, arrived at not through pure philosophical argument, but through some of the most carefully tested experimental physics ever conducted. The block universe, unchanging, containing all of history within a single, fixed, four-dimensional structure, sits remarkably close to Parmenides's ancient vision of an eternal, unchanging whole, with the flow of time relegated to the status of a perceptual aeon rather than a fundamental truth. Centuries later, the philosopher and theologian Augustine of Hippo, writing around the end of the 4th century, wrestled extensively with the nature of time in his work Confessions, posing questions that remain strikingly relevant to the modern physics discussion. Augustine noted the peculiar difficulty of defining time at all. The past no longer exists, the future does not yet exist, and the present, examined closely enough, seems to shrink to an instant with no actual duration of its own, vanishing the moment you try to grasp it. He concluded that time, whatever it ultimately is, seems to exist most clearly as something experienced within the mind, through memory of the past, direct perception of the present, and expectation of the future, rather than as a straightforward, external property of the physical world. This is, in a very real sense, an early version of exactly the same tension modern physicists and philosophers argue over today, whether the felt experience of time passing reflects something objectively true about the external universe, or whether it is primarily, or even entirely, a feature of how conscious minds process and organize information. What has changed since Augustine's era is not the fundamental shape of the question, but the tools available to investigate it. Where Augustine had introspection and careful reasoning, modern physicists have particle accelerators, atomic clocks precise enough to detect the effect of climbing a single stairstep, orbiting satellites, and mathematical frameworks tested against millions of individual experimental measurements. And remarkably, after all of that additional evidence, the deepest version of Augustine's puzzle, what time actually is, remains genuinely, rigorously unresolved. Given how much has already been confirmed experimentally, it is worth being precise about where the genuinely open frontier of this research sits today, because it is not in special relativity, which is about as thoroughly confirmed as any theory in physics, and it is not really in general relativity either, which has passed every experimental test thrown at it for more than a century, including the direct detection of gravitational waves by the LIGO collaboration in 2015, and the first ever direct image of a black hole's event horizon, captured by the Event Horizon Telescope collaboration and released in 2019. The open frontier sits specifically at the unresolved boundary between general relativity and quantum mechanics, the problem of quantum gravity mentioned earlier. And it is here that the deepest remaining questions about the true nature of time are concentrated. Several major research programs are actively working on this problem, each taking a different approach, and each with different implications for how time might ultimately need to be understood. String theory, developed initially in the late 1960s and expanded dramatically through the 1980s and 90s, proposes that the fundamental constituents of reality are not point-like particles, but extremely small, vibrating strings of energy, with different vibrational patterns corresponding to different particles we observe, including the graviton, a hypothetical particle that would carry the force of gravity in a fully quantum framework. String theory generally treats space-time, including time, as a fixed, continuous background that the strings vibrate and move within, though some more advanced formulations, particularly those involving a mathematical tool called the holographic principle, suggest that space-time itself, including its dimensionality and structure, might emerge from a more fundamental description that does not include space-time or time as a primitive ingredient at all. Loop quantum gravity, the framework most closely associated with Carlo Rovelli and physicist Lee Smolin, developed largely from the 1980s onward, takes a different approach, attempting to directly quantize the geometry of space-time itself, rather than starting with strings moving through a fixed background. In this framework, space, at the smallest possible scales, roughly 100 sextillion times smaller than an atomic nucleus, a length called the Planck length, is proposed to be discrete rather than smooth and continuous, made up of tiny, indivisible units, sometimes visualized as an underlying spin network, because loop quantum gravity treats space-time itself as the object being quantized. It naturally aligns with the idea that time might be an emergent, approximate concept, arising from the statistical relationships between these fundamental, discrete building blocks, rather than a smooth, continuous background flowing steadily in one direction. A third, less widely known approach, called causal set theory, developed largely by physicist Raphael Sorkin, starting in the 1980s, takes causality itself as the single most fundamental building block of reality, more fundamental even than space or continuous time. In this framework, the universe is modeled as an enormous, discrete set of individual events, connected to each other only by causal relationships. This event could have influenced that one, and nothing more. Distance, geometry, and the smooth passage of time that we experience are all proposed to emerge at larger scales, purely from the pattern and density of these underlying causal connections, echoing in a very different mathematical language the same light cone structure discussed earlier as one of the few things every observer in relativity actually agrees on. None of these three approaches, string theory, loop quantum gravity, or causal set theory, has yet produced a testable, experimentally confirmed theory of quantum gravity, and it remains entirely possible that the eventual correct theory, if one is ever found, will look quite different from any of them. But it is a notable and consistent pattern that essentially every serious attempt to unify quantum mechanics with general relativity ends up treating smooth, continuous, flowing time not as a fundamental ingredient of reality, but as something that needs to be explained, derived, or recovered from a deeper, more fundamental structure that does not obviously include it to begin with. On the experimental side, physicists have also directly searched for any sign that the perfect symmetry of relativity, the idea that the speed of light and the laws of physics look identical to every observer, regardless of their motion or orientation, might break down at extremely small scales or extremely high energies. A possibility predicted by some candidate quantum gravity theories. Experiments using the Fermi Gamma Ray Space Telescope have examined light arriving from extremely distant, extremely energetic astrophysical events called gamma ray bursts, checking whether photons of different energies, having traveled billions of light years, arrive at even very slightly different times, which would indicate a breakdown of the strict relativistic symmetry we have relied on throughout this discussion. So far, these searches have found no evidence of any such violation, placing increasingly tight constraints on how and at what scale any departure from relativity's predictions could possibly occur, and reinforcing rather than undermining the reliability of the core relativistic framework this entire block universe picture depends on. It is worth pulling all of these threads together into a clear summary of exactly what is settled and exactly what remains genuinely open, because the strength of this topic comes from being honest about that distinction rather than blurring it for dramatic effect. What is settled, confirmed by more than a century of increasingly precise experiments, is that time is not the fixed, universal background Newton imagined. Clocks moving at different speeds genuinely tick at different rates. Clocks at different heights within a gravitational field genuinely tick at different rates. Observers moving relative to each other genuinely disagree about which distant events count as simultaneous, without either of them being mistaken. And the geometric framework that explains all of this, Minkowski's four-dimensional spacetime, treats every point in that structure, including the moment of your birth and the moment of your death, as existing with the same basic mathematical status, neither one privileged over the other by anything in the equations themselves. What remains genuinely open is the deeper interpretation of what that mathematical structure actually implies about the nature of reality, and specifically why conscious experience seems to move through that structure in a single, consistent direction, remembering the past, anticipating the future, and experiencing a persistent, vivid sense of now that the equations of relativity themselves give no special role to. It remains open whether time is truly fundamental an irreducible ingredient of reality, or whether it is emergent, arising from more fundamental, timeless relationships between quantum states, entropy gradients, or causal structures, as suggested by researchers like Julian Barber, Carlo Rovelli, and the broader community working on quantum gravity. It remains open exactly how or whether the strict, fixed causal order that relativity insists on within a light cone can be reconciled with the genuinely blurred, probabilistic causal order demonstrated in quantum switch experiments. A tension sitting at the very heart of the unresolved conflict between general relativity and quantum mechanics. And it remains open why the universe began in the specific, extraordinarily low entropy configuration that set the entire thermodynamic arrow of time in motion in the first place. A question tied directly to cosmology's own unresolved puzzles about the earliest moments after the Big Bang and the true nature of the enigmatic dark energy now driving the universe's accelerating expansion. These are not small peripheral gaps in an otherwise complete picture. They sit at the absolute center of theoretical physics, and resolving them, whenever that eventually happens, would likely count among the most significant scientific achievements in human history, comparable in scale to the original development of quantum mechanics and general relativity themselves in the early 20th century. Multiple international collaborations spanning particle physics, astrophysics, and quantum information science are actively working on different pieces of this puzzle right now, using tools ranging from gravitational wave detectors capable of measuring distortions in spacetime smaller than the width of a proton, to tabletop quantum experiments manipulating individual photons, to space telescopes examining light that has traveled toward us for billions of years. Some of the most significant progress on these questions has actually happened quite recently, within the last few years. And it is worth highlighting because it shows this is not a stagnant field waiting for a single breakthrough, but an area of active, incremental progress happening right now. Around 2019 and 2020, several groups of theoretical physicists, including Ahmed Almhiri, Netta Inglis, Donald Murolf, Henry Maxfield, and Jeff Pennington, working somewhat independently, made significant progress on the black hole information paradox discussed earlier, using a technique involving what are called islands and a mathematical tool known as replica wormhole, building on foundational work by Juan Maldacena and others, exploring the relationship between quantum gravity and lower dimensional quantum field theories. Using these tools, researchers were able to calculate something called the Page curve, a specific prediction first proposed by physicist Don Page in 1993, describing exactly how the entropy of radiation escaping an evaporating black hole should behave over time if information is intact, preserved, rather than destroyed. For decades, calculating this curve directly from first principles had proven extraordinarily difficult. The newer calculations, published in leading physics journals starting around 2019, successfully reproduced the Page curve in certain simplified model universes, providing strong theoretical evidence that information is indeed preserved during black hole evaporation. Consistent with the core principles of quantum mechanics, rather than genuinely destroyed, as the simplest early treatments of Hawking radiation had suggested. This does not fully resolve the black hole information paradox in our actual, four-dimensional universe, since much of this progress has been demonstrated most rigorously in simplified, lower-dimensional model systems that are mathematically easier to work with, rather than in the full, realistic case. But it represents genuine, substantial progress on a problem that had remained largely stuck for decades. And it illustrates something important about how progress in this field tends to happen, not through a single, dramatic breakthrough that resolves everything at once, but through incremental, technical advances that gradually narrow down which of several competing theoretical possibilities is more likely to be correct. Parallel progress has also come from an entirely different, more experimental direction, sometimes called analog gravity, because it is currently impossible to directly experiment. Some physicists, including Jeff Steinhauer and his research group, have instead built laboratory systems using ultra-cold atoms, called Bose-Einstein condensates, that mathematically behave in ways closely analogous to the physics near a black hole's event horizon, including a laboratory analog of Hawking radiation itself, first reported in 2016 and refined in follow-up experiments since. These analog systems cannot fully replace direct observations of real astrophysical black holes, since they do not involve actual gravity or actual space-time curvature, but they allow researchers to test specific mathematical predictions, radiation, and entropy in a genuinely controlled laboratory setting, offering an unusual and valuable complementary approach to a problem that is otherwise almost entirely theoretical. Meanwhile, gravitational wave astronomy, made possible by the LIGO and Virgo detector networks, has opened up an entirely new observational window that did not exist at all before 2015, allowing physicists to study extreme space-time events, colliding black holes and neutron stars, directly. Through the ripples in space-time's geometry those collisions produce, rather than only through the light or particles they emit. Each new detected event provides another high-precision data point against which the predictions of general relativity, including its treatment of time near extremely strong gravitational fields, can be tested, and so far, across more than 100 confirmed detections, general relativity's predictions have matched the observed data with remarkable consistency. Given everything covered so far, it is worth returning to the specific claim we opened with, and stating precisely what it does and does not mean, now that the full physical picture is on the table. The moment of your birth is a fixed point within a four-dimensional structure that, according to the mathematics of relativity, does not privilege any one moment as more real, more present, or more now than any other. The moment of your death, whenever and wherever it occurs along your own world line, occupies its own fixed point within that same structure, with exactly the same status. From the perspective of the block universe, neither event is created or destroyed by the passage of time, because the equations governing spacetime give no indication that anything is flowing past these fixed points at all. In this specific, carefully qualified sense, every moment of your life, including its very first moment and its very last, already exists permanently within the structure of the universe, and always will. This does not mean, and this distinction matters enormously, that your death has somehow already happened from your own conscious perspective. robbing the intervening years of their significance. Your conscious experience still appears to move along your world line in a specific direction, forming memories of earlier points and not later ones, exactly as the entropy-based arrow of time discussed earlier would predict. Whatever ultimately explains this felt experience of time passing, whether it turns out to be a fundamental feature of consciousness, an emergent statistical phenomenon tied to entropy and memory formation, or something quantum gravity has not yet fully explained, the years, decisions, relationships, and experiences that make up your world line between those two fixed endpoints remain exactly as significant, exactly as consequential, and exactly as genuinely yours to shape through your own choices, as they would be under the older Newtonian picture of time flowing steadily from past to future. What changes is not the value or reality of your lived experience. What changes is the underlying explanation for why that experience takes the particular shape it does. Why the present moment feels so uniquely vivid and urgent, even though the equations describing space-time give no special mathematical status to any one moment over any other. That gap between the felt experience of time passing and the geometric structure the equations actually describe is precisely where the genuinely unresolved physics lives. And it is a gap that has resisted a full, agreed-upon explanation for more than a century, despite the enormous amount that has been learned about the structure surrounding it. Before closing, it helps to make time dilation concrete with the single most famous illustration of it, because it ties directly back to the idea of two different, equally valid world lines diverging and reuniting within the same block universe. Imagine a pair of twins. One boards a spacecraft capable of traveling at a significant fraction of the speed of light, journeys to a distant star, and returns to Earth, while the other twin remains at home the entire time. When the traveling twin steps off the spacecraft, they find that their sibling has aged considerably more than they have. If the traveling twin journeyed at 90% of the speed of light, for instance, a round trip that took roughly 22 years, as measured by the twin who stayed on Earth, would take only about 10 years, as measured by the traveling twin's own clock, and their own experienced aging, since time dilation would cause the traveling twin's clock, and every biological process running on the same physical timeline, to run correspondingly slower for the duration of the high-speed journey. This scenario is often presented as a paradox, because from the traveling twin's own perspective, it might seem like it is the earthbound twin who is moving, and therefore the earthbound twin's clock that should run slower instead. The resolution lies in recognizing that the two twin situations are not actually symmetric. The earthbound twin remains in a single, unaccelerated reference frame for the entire journey, while the traveling twin must accelerate to leave Earth, decelerate and turn around at the distant star, and then accelerate and decelerate again to return, undergoing several changes in velocity that the earthbound twin never experiences. This asymmetry, formally analyzed using the tools of special and general relativity together, breaks the apparent symmetry of the situation and produces a single, consistent, experimentally verified answer. The traveling twin genuinely ages less, an effect that has been confirmed in miniature. using precisely those atomic clocks flown on commercial aircraft that were discussed earlier in this same discussion of time dilation. Within the block universe picture, the twin paradox becomes a particularly clean illustration of a broader truth. The two twins do not experience a disagreement about which events are more real. Both of their world lines are equally fixed, equally permanent structures within the same four-dimensional block, running from their shared moment of birth to their eventual, individually determined moments of death. What differs between them is simply the length of each world line as measured along its own path through space-time, sometimes called its proper time, a quantity that depends on the specific path taken through the four-dimensional structure. Exactly the way the length of a road, measured along the road itself, depends on whether that road takes a direct route or a long, winding detour between the same 2 points on a map. So where does this actually leave things, scientifically, going forward? The honest answer is that physics has made extraordinary, rigorously tested progress on the structure of space-time, while making comparatively little progress on the much harder question of why conscious experience moves through that structure the way it does. Special relativity, confirmed through muon decay experiments, particle accelerators, and atomic clocks precise enough to detect the passage of a single stair-step, tells us with very high confidence that there is no universal objective now shared across the whole universe. General relativity, confirmed through gravitational time dilation, the direct detection of gravitational waves, and the first ever image of a black hole's event horizon, tells us with equally high confidence that time bends and warps depending on gravity and motion, in ways that make the moment of your birth and the moment of your death equally fixed, equally permanent coordinates within the same four-dimensional structure. These are not speculative claims awaiting future confirmation. They are among the most thoroughly tested results in the entire history of experimental science. What remains genuinely open and will likely remain open for a considerable time to come is the deeper question of quantum gravity, the unresolved relationship between the smooth, geometric space-time described by general relativity and the discrete, probabilistic behavior described by quantum mechanics. Competing frameworks, including string theory, loop, quantum gravity, and causal set theory, offer genuinely different pictures of what might lie beneath the smooth, flowing time we experience. And current experimental technology, while improving rapidly, has not yet been able to distinguish decisively between them. Progress continues incrementally through theoretical work, like the recent calculations of the Page curve using islands and replica wormholes, through analog gravity experiments using ultra-cold atoms in laboratory settings, through ever more sensitive gravitational wave detectors coming online in the years ahead, including planned space-based observatories like the Laser Interferometer Space Antenna, expected to begin operating in the 2030s, and through continued high-precision tests searching for any subtle breakdown of relativity's core, symmetries at extremely small scales or extremely high energies. It is worth being honest, too, about why this particular topic continues to draw so much sustained interest from physicists, philosophers, and curious non-specialists alike, without needing to manufacture any artificial sense of mystery around it. It sits at a genuinely rare intersection a question ancient enough that philosophers were seriously debating it 2,500 years before Einstein was born, modern enough that active laboratory experiments are refining the answer within the current decade, and personal enough that it touches directly on how every single person experiences their own life. Every single day, whether or not they have ever thought about the underlying physics at all. Few open questions in science manage to combine that particular blend of deep antiquity, cutting-edge experimental relevance, and immediate personal resonance in quite the same way. There is also a specific kind of intellectual satisfaction available here that is worth naming directly, because it is different from simple curiosity. Understanding the relativity of simultaneity, and following the chain of reasoning from the constancy of the speed of light through Minkowski's geometric reformulation to the conclusion that your own birth and death, equally real coordinates within a four-dimensional structure, is not simply learning an interesting fact secondhand. It is walking through, in a compressed and simplified form, one of the great logical achievements of the 20th century, a chain of reasoning built entirely from a single, carefully verified experimental observation, the constant speed of light, and a willingness to follow the mathematical consequences of that observation wherever they led, however strange the destination turned out to be. That is worth appreciating on its own terms, independent of whatever further discoveries eventually resolve the questions that remain. None of the open questions covered here. The problem of time in quantum gravity, the black hole information paradox, the origin of the universe's initial low entropy state, or the precise relationship between conscious experience and the block universe's fixed geometric structure, are likely to be fully resolved within the next few years. But each one is being actively worked on right now by researchers using tools and techniques that did not exist even a decade or two ago. And the history of this particular question, stretching from Newton's absolute time, through Einstein's relativity, through Minkowski's spacetime, through Gödel's rotating universes, and into today's quantum gravity research programs, suggests that whatever comes next will likely be at least as strange, and at least as illuminating as everything that has come before it. For now, the clearest, most rigorously supported answer physics can offer is this: time does not flow the way it feels like it flows. The present moment you are experiencing right now has no special privileged status written into the laws of physics, and somewhere within the fixed four-dimensional structure of the universe, the moment of your birth and the moment of your death already exist, permanently, side by side with every other moment of your life, not as memories or predictions, but as coordinates, exactly as real and exactly as fixed as this one.